So now what we're going to do is that we're going to identify what I is exactly. What is the content of our information I? So if I, let's say, is x less than x star, which is our threshold value, and it's uniformly distributed, we have a truncated distribution of this sort. Okay, so this is our threshold, and we know that we're somewhere here. So in the case that our patient receives the message low, his expectation is going to be that x is conditional on x being less than or equal to x star. X is going to either be 0 or x star over 2, because x is uniformly distributed. You take the limits and divide them by 2, which is then going to equal x star over 2. Should the patient receive the message high, his expectation is going to be x conditional on x star being less than or equal to 1, in which case we get 1 plus x star over 2. And now we have another truncated distribution. This is our threshold. One plus x star over 2. This is the patient's best reply when he receives a message. Now, how does the doctor best reply to y star so that we can satisfy the condition of sequential rationality? She is going to compare her payoff for y star low to her y star high payoff, given that he has a choice to send the message high or low for state x, whatever that may be. The utility of the doctor for sending a message low is going to be equal to minus x minus b minus y star, which we've already shown to be x over 2 squared. And his utility of the doctor for sending message high is going to be minus x minus b minus 1 minus x over 2 squared. We have to note before anything that the utility of the doctor is always negative, and of the patient is at most 0. So let's say that here goes our unit interval 0 and 1. If we take the first order condition of the utility function of the doctor for low, the best response, which is going to be b plus x star over 2. If we take the first order condition for this function, the best response for the doctor is going to be b plus x plus 1 over 2. Our quadratic equations intersect at the threshold. But let's run through the math now. So let's take the derivative of the utility of the doctor for low, which is going to be equal to minus x minus b minus a over 2, watch this, squared. I am taking x star and I am translating it as a because it's going to be confused with this x, so I'm just giving it another name. so it becomes less confusing. First, you simplify the expression, which will yield minus a squared over 4, and now I'm copying this from what I've done before, ab plus ax minus b squared plus 2b x minus x squared. Now we take the first order condition with respect to x, because that is what our doctor cares about. We arrive at a plus 2b minus 2x is equal to 0. Isolate x. However, we've got to retranslate this into x star. So what we get is x star plus 2b is equal to 2x. Divide everything by 2, which gives us x star over 2 plus b is equal to x, which is our best response x, which is going to be the best predictive estimate of low. If we do the same thing for the doctor, for sending the message hi is equal to minus x minus b minus, remember I'm changing x star into a squared. If it's simplified, we take the first order condition with respect to x, changing a into x star, please, so that we don't forget. And we arrive at an expression of minus x star minus 2b plus 2x minus 1 equals 0. 2x is equal to x star plus 1 plus 2b. We divide everything by 2 and we arrive at our solution. X best response to high, x star plus 1 over 2 plus b. This is the best predictive estimate of message hi. I need to construct x star, so we make the signal low a best reply when x is below x star, and a signal high a best reply when x is above x star. Looking at the graph, it is better to send message low when the utility of low is greater than the utility of sending message high. Where the curves intersect, utility for the doctor for sending message low is equal to the utility of the doctor for sending message high. Therefore, the doctor is indifferent, and that breaking point must be x star. And of course, there's only one intersection. So this is what we're going to check for. X star over 2 minus b is equal to b minus x star over 2 plus half. Now, I'd actually like you to solve this yourself. However, I'm going to give you a rule which is going to help you to solve it, where x squared is equal to y squared allows you to say that x is equal to y and that x is also equal to minus y. So using the rule that given you have an equation where x squared is equal to y squared, you can actually apply a solution with two equations. Say x minus b minus x over 2 is going to be equal to minus 1 x minus b minus x plus 1 over 2. Now, there's a particular trick that we need to use here. So we're going to multiply both sides by a constant. And this should then yield x over 2 minus b is equal to b minus x over 2 plus half. Now that we've arrived at our simplification, we've already equated them, we've simplified these expressions as much as possible, we're now going to solve for x star, the ideal or the highest utility that the doctor can achieve if his utility for low is equal to his utility for high. And that is going to be x star equal to 2b plus half. Separating perfect Bayesian equilibrium. Now what I want you to note about this expression is that the bias, now just look at this term here, it is only an equilibrium if b is less than or equal to a fourth. Otherwise, x star is going to be greater than 1. And in this case, it would contradict our initial assumption that x is included between the unit interval. Any solution outside of 0 and 1 does not hold when there are two possible messages. B must be less than or equal to a fourth. Therefore, the patient will implement the midpoint between 0 and x star for the low interval when the message is low, and the midpoint between x star and 1 for high interval when the message is high. Note that if there is no bias, right, imagine b is 0, they divide the interval into two equal parts. That the doctor wants to move the recommendation to the left of the true state of the world. That is why the bias is there. The doctor always wants to lie downwards. Now, this is a condition of the game that occurs because the intervals are ranked in order. Okay, so the partitioning happens in order, in ascending order. And therefore, wherever the state of the world is, the bias being positive, he will always want to recommend something to the left so he gets something closer to what he wants, or she wants in our case. In order to make the doctor lie downwards, we have to make the right interval larger than the left interval, or we have to make his loss, or we have to make her loss in the left interval larger than in the right interval. And this is why we use the bias to move the recommendation to the right of half. We make the information coarser. What we've discovered so far is that x star is less than 1. By construction, and for our equilibrium to hold, x star was equal to 2b plus a half. And this implied that 2b has to be less than or equal to half, which also meant that b is less than or equal to a fourth, which means the bias must be relatively small in order for separating equilibria to exist. So we find a very similar conclusion to the one that we had in the simpler version of the model. When bias is above a fourth, the only equilibrium has to be the babbling equilibrium. You cannot have any information flowing from the doctor to the patient. The patient essentially ignores the doctor.